So we're getting Pooya here from wherever he is remotely. Give us just a moment and we will begin.
Awesome. Thank you so much. So this is a joint Sahar Karmi, Sonia and Brad Wood from 1QBit. And I have the paper for your reference. And we've been thinking about pipeline constraint programming using a quantum mediator. So I would like to report that. I start with a motivation from penalty methods. So penalty methods are very successful for solving some classes of problems on a quantum computer, for example, maximum independent set, max type problems, things like that. But for example, in this example of a quadratic knapsack problem, we see that penalty methods would not be a very efficient method for solving the problem. The difference of this with a maximum independent set or Ising's spin glass model is that we have a knapsack constraint here. I've used the jargon from finance here just to indicate that this is actually a very useful problem to try to solve. What I want to point out is this value V, which is just a constant, which is the volume of the knapsack we're trying to solve. To be able to solve this using an Ising model, we have to go through a set of conversions. We have to get rid of the integer variables in the knapsack and create binary variables. Then we have to change the inequality constraint to an equality constraint. So this conversion would create coefficients for these slack variables, these binary slack variables, which would be in the order of this constant V, which is usually much larger than the coefficients that appeared in the interactions between the variables in the original problem. The situation becomes worse when we try to relax the problem with a penalty term, which creates a quadratic term in which every two variables in your problem get multiplied together. So if you did have sparsity in your problem, which is often the case in real-world applications, then you would need to be able to go for full connectivity, and also the precision requirements even increase more because now you don't only have to handle coefficients that are as big as V, but they should be as big as V times a sufficiently large penalty coefficient. So basically, this penalty method would go through a number of conversions, would just make the problem much harder to solve for a heuristic, including a quantum heuristic like quantum annealing. So the key idea is to instead of solving the penalty relaxation of the problem, to solve something that is called the dual relaxation of the problem. There are many dual problems. What I like to talk about is the Lagrangian dual. And the way it's formed from this original primal problem is that instead of relaxing every one of the inequality and equality constraints using penalty terms, what you do is that you multiply the slack of each of them, which is basically ax minus p, with a Lagrange coefficient. For inequality constraints, the Lagrangian coefficient has to be positive. For equality constraint, it could be any real number. And then we add this bilinear term to the objective function. So for a fixed choice of lambda and mu plus, we get a cubo, which we can solve with a quantum theory. The property of the Lagrangian relaxation is that the optimal value of it is a lower bound for the optimal value of the primal solution. So if we try to maximize over all choices of lambda and mu, we get the tightest lower bound possible by the Lagrangian relaxations, the family of them. And this problem is called the Lagrangian dual problem to the primal problem that we've been trying to solve. Usually this is very hard to solve. In classical algorithms, almost never this is used. What happens is that you first have to relax your binary variables to a continuous domain and try to solve the dual problem. But if you don't do that, try to take advantage of something like quantum annealing to solve these Lagrangian relaxations, what you get is a much tighter lower bound, which is a bit of an approximation for the primal problem you were trying to solve. There are many ways to solve this problem when it's discrete in terms of the binary variables. And basically, the way to do this is the Lagrangian dual problem is trying to find over all points in this convex undergraph that is determined by all the cuts that you generate from the different choices of the primal variables. You want to find the highest altitude. So you can imagine that this could be done with a gradient descent method, where the values of the gradient come from, for every choice of the Lagrange multipliers, they come from solving a cube at that choice of the Lagrange coefficients. Another way to solve it is using cutting planes, where you start from some choice of the Lagrange multiplier, you solve a cubo. So for example, if you solve it at 0, you will get this cut. You add the cut to the dual problem, and then you iterate over this to create all the relevant cuts, the ones that are actually drawing this polytope. And the point is that you don't end up having to construct all of them. You always end up having to construct a polynomial many of them if the problem is well conditioned enough. And that will create an efficient method for solving the Lagrangian dual problem. Okay, so we wanted to test the idea of using this tight Lagrangian dual bound to solve a problem. And to do that, we looked at a problem where the solution of the Lagrangian dual would actually solve the primal problem. And that's not always the case. When this happens, it's called strong duality. And to find a good example that is applicable, we looked at problems that are close to maximum independent set. So maximum independent set itself is a problem that it's useful to solve it using penalty methods, basically because this X transpose AX, which comes from A being the adjacency matrix of the graph you're trying to solve, is positive. So you don't end up creating quadratic terms when you use the penalty term. Also, the coefficient in this penalty term only has to be a little bit more than 1/2, and you would be good to go. So the problem we're looking at has the same independence constraint, but also another quadratic constraint, which is also an independence constraint, but you can think of this as being a soft constraint and the adjacency being a hard constraint. So this appears in scheduling problems, for example. So we were able to use the same logic that draws this 1/2 bound for the maximum independent set to find the tightest theoretical bound we can find for this problem. And so the formula looks a little complicated, but all what you want to know is that the value of the penalty term you have to use here is in the order of the row sum of this matrix W. So if the problem is well conditioned enough, you can imagine that this penalty term would grow linearly in the number of variables, for example, in the original problem. You can do a little bit better if you choose a different penalty term for every entry, every edge of the matrix, but it's still in the order of the row sum of W. So when trying to solve this problem using D-wave systems, if you fix every choice of the Lagrange multiplier, which is basically, in this case, it's the same as the penalty coefficient. So the dotted line on the right-hand side of each graph is this tight penalty, theoretical penalty. And we don't see the solution at all when we try to solve it with this penalty method. But there are many choices of the dual variable for which we see the solution with with a high success probability. And the reason for that is that for specific instances, the places at which the optimal primal dual pairs appear are much lower than when you use the penalty term, when you use the theoretical penalty coefficient. So we went ahead and used this idea to create different gradient descent methods to solve the Lagrangian dual problem. So the first two columns, so these are instances of size 30 for this generalized quadratic stable set problem. The first two are when we use the two propositions that I talked about. And these columns are showing our learning curve in understanding how to do a good job in making the gradient descent for solving the Lagrangian dual problem using D-wave systems. So you see that this hybrid method of basically a linear step sizing and Newton method for gradient descent almost always solves the problem, whereas the penalty methods almost never solve the problem. We solve the same problem using SQA, and we get very consistent numerical results in the success of solving the problem using the Lagrangian dual map. Okay, so to create a pipeline for solving constraint problems in general, what we think is that we like to have a branch and bound scheme where the branching and upper bounding is happening classically on a classical computer. The branching is happening over the binary variables, but at every node of the branch and bound tree, we would solve this quantum lower bounding problem using the Lagrangian dual. And because this bound is much tighter than what you can get from classical dual problems, you would be able to prune a lot more of the tree inside the branch and bound tree. Of course, this would require a hybrid method. So you would have to have less communication lag between the classical and the quantum computer. But I think we're getting familiar and used to hybrid methods, at least for near-term quantum algorithms in quantum chemistry applications, in QAOA, in quantum machine learning. But I also want to point out that even in far future algorithms, you would still want to have a hybrid platform of digital processing units and quantum processing units, for example, in error correction applications. Okay, so the advantage of solving this Lagrangian dual instead of the penalty term is that we have a lot of freedom in allowing these Lagrangian multipliers to, for example, be bounded by the precision that the QL solver is giving us, or they don't have to even be in a continuous domain. We can discretize them as much as we are allowed by the precision. And the most important thing is that it preserves the density of the original problem. Of course, the disadvantage that I talked about is that we'll have some communication lag. And if you have a noisy solver, what happens is that you could end up with a wrong choice of the lower bound, which can prune the wrong parts of the tree. So we won't exactly be able to create an exact solver if we don't have good understanding of the noise of the system. So these are numerical experiments for solving problems with anything between 36 to 50 variables, and half of that is chosen as the number of constraints. The first few columns are different branching strategies for the branch and bound algorithm that I talked about. And the last one is the number of nodes that Gurabi solver, which is the classical algorithm, has to go through. So we see that when we go just from 36 to 50 variables, the number of classical nodes that you have to travel through goes from tens of thousands to millions, whereas the number of nodes you have to travel in branch and bound using the LD-based method stays in the order of less than 100. What this means is also that if we look at this notion that we called annealing leniency, which is basically the amount of time you have for every, on average, for every call to the quantum annealer, the amount of time you're allowed to waste on every call, so that you're still comparable to the classical solver or outperforming it, is growing exponentially. So, for example, for problems as small as size 50, you can spend about a second to solve each of the problems with all the post-processing and pre-processing, and you would still be outperforming a classical solver. Okay, so the last point that I have to talk about in this pipeline for integer programming is we talked about the constraints. I have to also talk about how to handle the integer variables. So the idea here is that we want to, instead of using binary encoding, which has these coefficients that are basic powers of 2, we want to have something that we call bounded encoding, where the bound is given somehow with the noise model of the system. So in this example, if I want to encode everything between 0 to 12, and the largest coefficient I'm allowed to use is 8, basically the idea is very simple. We just start with the binary encoding, and we go up to the point where we can't go higher than the allowed coefficient, and then we fill the rest of the coefficients with the remainder between what we can encode with the binary encoding we use and the and the integer we want to be able to encode. So obviously the hard problem is finding this upper bound mu, given by, for example, some noise matrix for the local biases and the couplers of the system. If we try to make an optimization model for finding each upper bound for each of the integer variables, and unfortunately, what you get is a non-convex problem. It's very hard to solve. However, all credits to Sahar. She found a very nice heuristic for solving this problem in a very efficient and greedy way that will give us the upper bounds for each of the integer variables. And so the test with it for this was actually suggested to us by Helmut Katzgraber. So the idea is to look at the two encodings that I just talked about, basically the naive binary encoding and our bounded coefficient encoding, and try to add some Gaussian noise to the couplers after the encoding, and see for what percentage of the problems the optimal solution has shifted from the original problem. And that's called the resilience of the problem to noise. So we see that when we use the binary encoding, very soon almost all the optimal solutions have shifted from the original problem, whereas the bounded coefficient encoding is much more resilient to this type of noise. So we think that would be that would give us a nice way to use a noisy QUBO solver for integer programming with this idea and the ideas that I talked about for constraint programming. So that is my last slide. I answered questions.
So if you have a question, I would like you to come actually up here and talk directly to the Skype call, because we only have a mic in there.
Hi, Pooya. This is Andrew King. Nice to see you. I was wondering if this Lagrangian dual preserves the embedding structure of the problem, because I know that maximum independent set has a very nice embedding, so there's not a lot of overhead. Does that stay the same when you do the dual?
Awesome. Yeah, that's a very good question. So if the original problem we want to solve, and just quickly, if you're still seeing the slides, so if the problem we want to solve has a linear inequality and equality constraints, then the embedding only comes from this quadratic terms. So we only have to, so in the branch and bound, we only have to solve the embedding problem once. And every time we have to solve a new problem in these iterations for the Lagrangian dual, we only have to change the local field biases for different qubits. So this will preserve this structure when you have linear constraints. But there's no reason not to be able to solve quadratically constrained quadratic optimization problems with this method. Obviously, those are way harder problems to solve, even classically. If we do that, then the embedding would be imposed by the inequality constraints here. So it's basically the adjacency matrix is the union of the adjacency matrix from Q and the ones that are given by the constraints, and then your embedding is still preserved. So you only have to solve that problem one time, but the updates come over the couplers and the local field biases at the same time. Thank you.
And go ahead and put this on so you can hear more clearly.
Hi, Pooya. It's Kathy McHugh. So thinking about this quantum lower bound on your branch and bound, you pointed out that it's maybe not a lower bound, and I wonder if there's anything that can be done to, like, do you do anything to adjust for that? Like maybe just multiplying by an error factor, or maybe trying to solve a different problem that would give you a truer, a more reliable lower bound?
Nice. So that's also a very good question. So there are many branch and bound frameworks which are not exact solvers. They still give you a heuristic solution, and you can think of them as a heuristic for creating cuts, and divide the problem and conquer different parts of it. But yes, so if there's a lot of noise in the system, then you would not get in specific nodes. You can get wrong lower bounds. If the noise model is something like a Boltzmann distribution, then that's actually great because this motivates solving machine learning problems using this Lagrangian dual. For example, when you work with support vector machines or structured support vector machines, you would be able to solve this problem actually even more efficiently. So there is a work in progress by a group in 1QBit on solving these problems that specifically arise from machine learning and statistical learning using this noise model. But if the noise model is not a Boltzmann distribution, meaning you don't get unbiased samples from the gradients of the problem you're trying to solve, then what you have to do is probably do something like R99 on the problem, or like analyze how much lower than the dual bound that is reported you have to go to stay safe, so that you don't prune too much of the branch and bound tree. So the second idea I haven't explored, that might be a nice work for someone.
Okay, so even though he may not hear us, let us thank him again.